So, we have talked about the elastic properties of bodies of solid materials. One thing that we haven't touched upon and are quite important and in fact, is very important in the context of this discussion is the effects of temperature. So, the temperature has been put out of the discussion so far, and now we are going to talk about temperature effects on these properties that we have just discussed, such as elongation, such as the stresses, etc. And think of a metal such as a steel bar being subjected to a change in temperature. Say the temperature increases from 100 degree centigrade to 200 degree centigrade. So, what is going to happen to the material, and what effects would it have on the thermal stresses and their corresponding applications, etc. So, let us talk about or rather make the discussion a little more quantitative by saying that let us see this. So, there is a rod, metal rod, which has an initial length L0, and when it is subjected to a temperature difference, say for example, delta T, it could actually increase by an amount delta L. Okay. And there are very familiar examples, such as you might have seen that there are small gaps in the railway tracks. Those gaps are kept to accommodate the change in length or the elongation of the rail track, the material of the rail track that it is made of. So, in this particular case, say the temperature goes from an initial Ti to a final temperature Tf, and the length of this bar, which is constrained to actually increase in the direction where it is hinged. So, this is hinged say in a, against a wall, which we at this moment we ignore the expansion of the wall due to this the heat that it is subjected to, and this has caused some stress in the material, and it is in the line of the discussion that we had, that either you apply a force in order to cause an extension, or you can also apply a change in temperature for the material to undergo an elongation, or if you actually lower the temperature of the body, it could actually undergo a compression, and in any case there will be a stress that is going to be developed, and this stress we will call as thermal stress for reasons that you would see just in a while. So, let us take this temperature difference Tf minus Ti to be called as delta T, and not only that, it should be small, it is not large, and in this case the change in length delta L is given by L0, and you have Tf minus Ti, and there will be a proportionality constant, let us call it as alpha, and just to make sure that this elongation happens due to the change in temperature, we put a subscript T here, and this is called as the linear expansion of solids, where the material under the application of heat, the temperature increases from Ti to Tf, and the coefficient linear coefficient of expansion is given by alpha, and L0 is the initial length before the temperature difference being applied is given as L0. So, this can be written as alpha L0 and delta T. So, my change in length is given by alpha L0 and delta T, and so if we want to understand that, so what is alpha? Alpha is called as the linear coefficient of expansion, it's a linear coefficient of, if you like, it's a thermal expansion. And which actually appears as a proportionality constant in this equation, and it has let us check the units and dimensions of alpha. So, so delta L will have a unit of say for example length, and alpha is something that we want to find. L0 again has the unit of the dimension of length, and delta T has say the dimension of temperature, which could be in either in degree centigrade or in degree Kelvin or in Kelvin, I am so sorry, in Kelvin. So, alpha is 1 over temperature, which we usually say in per degree centigrade, if you are talking about centigrade. So, so alpha is expressed in per degree centigrade, L0 is the initial length which is known, delta is the T is the temperature difference, and that causes an elongation of amount delta L T. Now, this has to be compared with the quantities that we know, and remember this delta L that we have talked about earlier under the application of tensile or compressive strengths, and this is given by compressive stresses. So, this is given by F L0 divided by A y. Just to remind you, F is the applied force, L0 is the initial length, A is the area of cross section of this rod, y is the Young's modulus, and if we equate delta L to delta L T, then we can equate the right hand sides as well, and we can write alpha L0 delta T, which is equal to F by A and L0 y. Clearly, L0 will cancel from both sides, and we can write F over A as sigma, and so this becomes equal to, so sigma can be written as alpha y delta T, and sigma is known as thermal stress. Just a few minutes back we were discussing that why it is called as a thermal stress, because now this depends upon temperature. Sigma, which is a thermal stress, depends on temperature, and rather it depends on the change in temperature, which is temperature difference between the final and the initial values. It has to be kept in mind that alpha and y both are taken to be temperature independent, which is true for delta T to be small, that is the change in temperature is not large, if the change in temperature becomes large, then we can have temperature dependencies coming in y or alpha, which we do not want to discuss. That is beyond the linear regime, and this will be treated as the thermal stress, which is now takes the place for mechanical stress, which had been generated by an application of a force, and now this sigma is generated because of the application of heat and thereby changing the temperature. So, let us do an example problem which will make things clear for you. So, we will write down the problem here. So, it is about these familiar examples of rail tracks and the small gaps that they have in between. So, let us take this so pieces of rail track each 10 meter long are laid with a clearance of 5 millimeters at a temperature °30 C. So, the first question is, at what temperature do the pieces just start touching? And the second question is, what is the thermal stress generated or developed if there were no clearance it is given that alpha is equal to 18 into 10 to the power minus 6 per degree centigrade, and the Young's modulus of the rail tracks, that is a material forming the rail tracks, is 200 into 10 to the power 6 Newton per meter square. Okay. So, I hope the problem is clear, that you have these pieces of rail tracks which are to be laid down in order for the trains to run on them, but as you know that they cannot be put right next to each other without having any gap, because in summer, where in many places in India the temperature goes up to 45 or even nears 50, the material will expand, and when it expands, you do not want the tracks to be actually putting a lot of stress on each other, in which case they may crack, and if they crack, that could cause accidents, which is what should be avoided completely. And in order to do that, they have kept small gaps in between, so that even if in summer they expand and come closer to each other, they should not cause stress. and that is how they are designed. And again in winter, where many of the places go up to a temperature of say 4 to 5 degrees or even lower than that, the contraction should go should take them apart, but shouldn't take them apart more than the desired distance, which could cause actually a gap in the rail tracks, which is inconvenient for the for these materials. So, for these rails. So, let us just write down all these quantities that we have. We have L0 equal to 10 m, we have delta L T which is 5 mm. Once again I remind you that this T stands for temperature, delta L is of course the elongation or the compression, in this case is the elongation, and the Ti that is given is equal to 30 degrees centigrade. And in the first part of the question, which says that at what temperature do these pieces start coming closer, that is they just touch each other, which means that they fill for this 5 millimeter of gap that is there, and so that is the first thing. And the second thing is to find out what is sigma, which is asked in the second part of the question, which says what is the thermal stress developed if there were no clearance. So, had there been no clearance, they would have expanded and caused stress, thermal stress, and which, as I told you, that which could lead eventually to breaking of the material, depending on the properties, the hardness and the toughness of the material that we have talked about. And now, let us just try to do this. I am clearing our part of this question. So, now all these quantities that are required to calculate are given here. The linear coefficient of thermal expansion is given as 18 into 10 to the power minus 6 per degree centigrade, and so is the Young's modulus that is given there. So, now we have to calculate delta L T, which is equal to alpha L0 delta T. So, your delta T that requires for my 5 millimeter of the delta L to be covered, which is equal to 5 into 10 to the power minus 3 meters. So, delta T, which is equal to delta L sub T divided by alpha L0, and if you put everything 5 into 10 to the power minus 3, and this is 18 into 10 to the power minus 6 multiplied by 10 meters, and this comes out approximately as 28 degrees centigrade, which means that the delta T, which is equal to T f minus T I, is equal to 28 degrees centigrade, and which means that T f is equal to 30 degree, which is the initial temperature, plus 28 degree, which becomes equal to 58 degrees centigrade. That means, at a temperature of 58 degrees centigrade, this 5 millimeter of gaps will get completely covered, which means will completely close, and this will cause of course a problem. So, let us see the next part of the problem, which is about calculation of the thermal stress, and in which case, as we understand that the thermal stress is computed from thermal stress it is equal to sigma equal to alpha y and delta t, alpha being 18 into 10 to the power minus 6, y is 200 into 10 to the power 6, and delta T is 28. So, when you put together everything, it comes out as 1008 Newton per meter square. So, just a quick understanding of this, had there been no gap kept while designing the rail track, there will be a stress, thermal stress, which is more than 1000 newtons per meter square that would develop where a temperature difference of 28 degrees is induced. So, this is a large stress, thermal stress that is going to be developed in the rail track. So, let us carry on with some more problems on thermal stresses and the effects of temperature. So, let us say a bronze bar (5 meter) long and a cross sectional area of 200 meters square is placed between two rigid walls as shown. So, there are two rigid walls . There is a bronze bar which has an initial length of 5 meter and there is a gap of 20 millimeter. So, there is a gap of 20 millimeter with the right wall and this happens. So, at a temperature minus 10 degrees centigrade, the gap between the bar and the right wall is 20 millimeter. The question is find the temperature, find the temperature at which the compressive strengths, the compressive stress in the bar will be 30 into 10 cube Newton per meter square, and given alpha, which is the coefficient of thermal expansion equal to 12 into 10 to the power minus 6 per degree centigrade, and y, the Young's modulus equal to 80 into 10 to the power 6 Newton per meter square. So, just to summarize the problem, there are two rigid walls and a bronze bar is tied with the left wall with an initial length of 5 meters. There is a small gap of 20 millimeters with the right wall, and this is the story at minus 10 degree centigrade. The question is, at what temperature there will be a compressive stress that will develop in the bar of this magnitude 30 into 10 cube Newton per meter square, and the coefficient of thermal expansion and the Young's modulus are given. You have to understand one thing in this problem, that the compressive stress of 30 into 10 cube Newton per meter square will come into the picture only when the rod will grow by 20 millimeter and will try to expand beyond that because of thermal effects, and then this stress will come into picture. So, at this situation there is no compressive stress, because the compressive stress will come from the when the bar will touch the right wall and will try to extend farther. So, we have to find that extension because of which the compressive stress is developed. And to find that, we can take a note that this must be the stress versus strain graph. I mean, we are assuming that Hooke's law is valid and we are not going beyond the elastic limit, in which case a strain of delta x will be generated, which is strain into L0, because the definition of strain is delta x by L0. So, a delta x is equal to strain into L0, and that from the linearity relation of the stress versus strain graph. We know that y, which is the Young's modulus, is the stress versus strain. So, this is equal to stress divided by y into L0. So, this stress is the compressive stress that the question has talked about. So, if I put all these values, 30 into 10 cube Newton per meter square divided by the Young's modulus, which is 80 into 10 to the power 6 Newton per meter square, into a 5 meter, this will give me a 1.875 into 10 to the power minus 3 meter. Understand that this is the extension which will happen when the rod has expanded by this 20 millimeter, and because of the thermal effects it will try to expand even more, and there will be a compressive stress that will be developed. So, now I can put it into this formula, which is equal to L equal to L0 1 plus alpha and Tf minus Ti, where Tf is the final temperature which is asked for, and Ti is the initial temperature which is equal to minus 10 degree centigrade. So, this will be so it is L minus L0 divided by L0 is alpha and a Tf plus 10 degree centigrade. So, putting all these, so L minus L0 is so L is equal to 5 meter plus 20 millimeter plus the delta x that we have calculated. L 0 is equal to 5 meter plus 20 millimeter. Thus, L minus L 0 is simply delta x. So, delta x divided by L 0 which will now have to be taken into account, and we now have 1.875 into 10 to the power minus 3 divided by 5. This is equal to 12 into 10 to the power minus 6 and a TF plus 10 degrees centigrade. So, if one solves for TF from here, it will come as 21.25 degrees centigrade. So, it is at this temperature the bar will not only will touch the right wall, but it will also start putting pressure on it, because of which the compressive stress will be developed, which is given by this, and this will happen at this temperature at 21.25 degrees centigrade, and the initial temperature was given as minus 10 degrees centigrade. So, let us do another problem. So, a cylindrical specimen of a certain alloy having Young's modulus with a diameter .9 millimeter, experiences an elastic deformation when a tensile load of 2000 Newton is applied. Calculate the maximum length of the specimen before deformation if the maximum allowable or rather maximum allowed elongation is 0.42 mm. So, just to repeat the entire question once again, a cylindrical specimen of a certain alloy which is a mixture of different substances having an and Young's modulus to be 108 into 10 to the power 6 Newton per meter square with a diameter of 3.9 millimeter experiences an elastic deformation. So, we are still in the elastic limit when a tensile load, which is a force of 2000 Newton is applied. So, calculate the maximum length of the specimen before the deformation, which means that the original length is asked for if the maximum allowed elongation is 0.42 mm. So, delta L is given to be 0.42 mm. So, for this cylindrical specimen, your initial area of cross section is equal to pi and a d0 by 2 whole square, which is like a pi d0 square over 4, where d0 is the original diameter By original, I mean that before the extension, and A0 is the original area of cross section. So, we have to calculate L0, the original length, that is the length before deformation. So, L0 is equal to delta L into y divided by sigma, where sigma of course is equal to F over A0. F is given to be 2000 Newton. So, if we put in all these things, 0.42 into 10 to the power minus 3 into 108 into 10 to the power 6 divided by 2000 into 4 into pi and 3.9 into 10 to the power minus 3 whole square. This comes out to be 0.257 meter, which is equal to 257, sorry, this is millimeter, this is 0.257 meter, which is equal to 257 millimeter. So, that is the original length of the sample. So, let us now talk about the energy stored in an elastic solid. See, we compress the solid under some tensile force and we elongate the solid under some compressive force, etc. And in order to do that, some work is done, and the work that is done against this elastic forces that we have discussed earlier, that is there inside the material, for deforming it, is a measure of the elastic potential energy that is stored in the sample. Okay? Upon again recovering back the original shape, the elastic potential energy is recovered. Okay? So, let us try to calculate this potential energy that is stored, and the best example to do that is, let us talk about a spring. And also let us constrain ourselves to the elastic limit, that means Hooke's law is valid. And where we have the force to be proportional to the elongation, let us write it for the moment as x. So, this is the force that is applied, and this is the elongation or the compression, and we can write this as kx. And we have to also put a negative sign, because just to make sure that the applied force and the displacement are taking place in the opposite direction. So, this is like a restoring force. So, it restores the normal configuration of the body. Now, if we try to calculate the work done, which is also the potential energy stored. So, this will be given by F dx, and at this moment let me take the magnitude of the force, because we are just going to calculate the work done, magnitude of the work done, and this is going to be kx dx by between some 0 to some maximum displacement or elongation x, and this is half k s square. So, this is the elastic energy that is stored in the deformed body. So, if you look at the stress strain curve, so or rather let us look at the force versus the displacement curve. So, this is the linear line which talks about this F equal to kx. We are ignoring the negative sign for the moment, and the work done, or equivalently the potential energy stored, let us write it with a u, is half k s square. Similarly, if you are talking about a shearing force, suppose a cylinder, an upright cylinder of like this is given a shear, and there is a deformation, angular deformation that is caused to be say theta, then the force is equal to g a theta, where g is the shear modulus, as we have discussed earlier, a is the area of cross section, and theta is the angle of shear. So, again your dx will be equal to L d theta, where L is the length of the cylinder or height of the cylinder. So, again the work done or the potential energy stored is given by g a theta and the L d theta, which will be written as half g a L theta square. So, these are the energy expressions for energy stored for a shear as well as in a spring for a linear extension of the amount S. Let us look at applications of elasticity on different components of human body, which is an interesting thing to look at, because even inside our body there are a lot of materials, or rather a lot of components which display elastic behavior. So, let us start with the bones. The bones, as you know, are the more weight bearing structures. I mean, they bear a lot of body weight that we have and a lot of activities that we do. You have seen those examples of a circus in which a person who does stunts, he can support a weight of 6 people on top of him, and his femur bones only get compressed by 10 to the power minus 6 meters, which is quite negligible. And these shocks or these pressures or these weights are actually supported by cartilages that are there in between the bones. So, let us talk about the femur bone. The femur bone is designed to bear a lot of weight, but even these bones do fracture, and the fracture is mainly due to applying of stress in a direction in which they are not supposed to bear the stress. So, it is in a wrong direction if a stress is given or a stress is generated that can actually break the bones. And so, no matter how well designed the human body is, if there are stresses given at wrong postures, then they will sort of break or they will rupture. So, let us talk about other materials where the strength is not all that important, but what is important is about their stretchability or their elastic properties. Such materials are the arteries and the veins. So, let us just list them. So, we have talked about bones. Now, let us talk about arteries and veins. So, the arteries and veins are supposed to carry blood, and the fact that blood is carried smoothly through the arteries or the veins, because the inner walls of the arteries and the veins are elastic in nature. And because they are elastic, when the blood flows, they accommodate that extra pressure that is generated by the pumping of blood, say by the heart. And similarly with the veins, the internal walls of the veins are also have elasticity, because of which the flow of blood is smooth. There are other materials where there are which also has components which have elasticity, such as the lungs and the tissues. They are the elasticity of lungs, as we know, plays a major part in our existence. That is, the lungs has to pump air, and that pumping, efficient pumping of air is crucially dependent on the elastic properties of the lungs. And as we age, the walls of the arteries or the surface of the lungs, they lose elasticity and the walls get hardened, which create trouble into their normal functioning, as we know that when a person grows old, all these problems are likely to occur. Also, the other stretchable components that we have are the muscles and the skin. And if one gets hurt, there is a swelling, and that swelling is because the skin has some elastic property. And over a period of time, the swelling goes down and the skin comes back to its original configuration. You must have seen really old people, the skin loses a lot of elasticity as people grow old. And so, by and large, what we are trying to say is that there are the components of human body also has a lot to offer regarding the elastic properties of matter. However, the stress versus strain character that we have seen earlier in case of solid materials differ a great deal with the components that we have just discussed of the human body. So, the stress versus strain curve can actually differ significantly from what we have learned, and each of the crystalline solids or the solids that we have learned, they have a generic behavior of the stress versus strain, while each of the physical components that we have talked about, such as bones, such as about lungs, about the arteries, veins, skin, etc., they can have very different stress versus strain relationship as compared to each other. So, let us see a typical stress versus strain relationship of a wool fiber. Okay. The sweaters are made of wool, and let us see that what kind of stress versus strain relationship they could have. So, this is the familiar graph that you have. So, this is stress and this is strain, and it goes like this. So, this part is somewhat known to us up till this, and then of course, it becomes flat for quite a while. That is application of stress is not, there is no application of stress. However, the strain keeps changing, and suddenly after a certain point the stress becomes large without significant increase in strain, and this is very different than what we have learned so far. Before we conclude this chapter on the elastic properties of matter, let us recapitulate the things that we have learned and list out some of the things that are important for our discussion. So, we have in the context of the elastic properties, we have learned Hooke's law, we have learnt about different kinds of elastic moduli, such as we have learnt about Young's modulus, bulk modulus and shear modulus. Stress versus strain curves in order to show that how the elastic limit is defined, and when do we actually talk about going beyond the elastic limit and talk about deformation. In that context, we have also discussed the difference between elastic, inelastic and plastic deformations. We have listed down a number of properties that are related to elasticity of a body, such as properties such as toughness, brittleness, etc. Elastic properties of human body, where we not only discussed about the strength of a particular component, but also we have talked about the stretchability of different components of human body, which are essential for normal functioning of the body. So, a few important points to mention and to ponder about are the following. Before we end this list, we should also talk about a number of example problems. So, we have looked at all these things one after another in the last 3 classes that we have studied elastic properties of matter. So, write points to ponder. So, in order to list out a few things which you should remember and which may go against the common sense sometimes, and you should keep it in mind. One of them is that so a material having large y is Young's modulus, it requires a large force, to produce a small elongation or compression. In fact, the second point is quite interesting, and it is often thought that the material which stretches more is known to be more elastic, and this is clearly a misnomer. The actual technical definition is that the material which stresses, which stretches or of course compresses to a lesser extent due to a given load is termed as more elastic. So, this second point has very important consequences, because it tells that a steel is more elastic than rubber, because under the application of a given load, a steel stretches or compresses by definitely a smaller extent than a rubber specimen. Third, which is important and subtle, is that stress is not a vector quantity. Unlike force, even though it is force divided by the area, it is not referred to as a vector quantity. In fact, because to talk about stresses, either it is if it is compressing, then we call it as a compressive strength, or if it is expanding, we call it as a tensile strength. All these terms are coined to show the stresses being developed in materials which are either going outward for a tensile or going inward for a compressive stress.